Hi, let's take a look at the last objective in this section, which is to use the intermediate value theorem to help locate zeros of polynomial functions. This is really kind of a brief concept, and after that I'm going to show you how we're going to bring all of those things that we've already discussed in this section together to graph a polynomial function. So let's first begin by kind of thinking about what the intermediate value theorem tells us. And it says that if you have two values, a and b, they're real numbers, where a is less than b, and f is a polynomial function. F of a does not equal f of b, so that means it's not one-to-one at that function or at those values. Then in the interval from a to b, the function f takes on every value between f of a and f of b. You're probably thinking, what? I don't really care, but it is kind of a neat thing to take place with some polynomial functions. So I've drawn a graph, not really to scale, and it doesn't really matter what a and b are as long as your a is less than b. So here we have a is less than b, right, because a is to the left of b. We have a polynomial function, so we know it's a smooth, continuous graph. And we know that the output values, the y values, are different. So I have a kind of a picture of what you can think in your mind of what this might look like. So this is saying that in between a and b, the function f takes on every y value between f of a and f of b. Where that's really important is in this way. If a and b have output values that are opposite, in other words, a has maybe a positive or negative output, b has the opposite of that, then what we know is that there has to be a zero between a and b. So we'll write it like this: if f of a and f of b have opposite signs, then there is a zero between the a and b. Okay? Think about that, because in a polynomial function, if you go from a negative output to a positive output, that means that you're crossing the x-axis. And so there has to be some zero between the a and the b. So there's some point c between a and b such that f of c is equal to 0. So I have brought in a table from the graphing calculator of a polynomial function that I entered, and I want you to use it to examine to tell me if you can find out if there's some zeros on this particular function. I didn't tell you the function for a reason. It doesn't really matter what it is because it's more the interpretation. So notice how we're looking at the y values first, because we're wanting to find out if there's any sign change in the y values, because wherever there is a sign change, there's a zero. So we are negative, negative, and then notice we go from negative to positive. So if you think about plotting that point -2, -14, and the point -1, 6, well, what would happen? -2, -14, -1, 6. In between there, it's going to do what? Cross the axis. So that means somewhere between -1 and -2, there is a 0 of f. And then it stays positive, positive, and then notice again it goes to a different sign. So that also means between 1 and 2, there's going to be a 0 of f. Okay, so a neat thing. Sometimes when you're trying to approximate zeros of a function, you can look at the table and know exactly where it's going to lie between if it's not an integer value, because then those are harder to approximate, right? So then you could fine-tune your calculator. You could go to second table set and change your table increment to, instead of changing by 1, maybe change it by 0.1, so you could literally zero in on that 0. So much for that. Now let's go to actually putting all this together. and graphing these polynomial functions. So there's basically 4 steps to graphing a polynomial function. The first thing that you need to do is apply the leading coefficient test to determine the end behavior of the graph, find the zeros of the function, and then plot a few additional points and draw the graph. So let's see how that process would be applied here. We have a function f of x is equal to x cubed plus 3x squared minus 9x minus 27. So what about the leading coefficient test? What does that tell us? Okay, so the leading coefficient is 1 because that's the coefficient of the highest degreed term. That degree happens to be what? 3, which is odd. So we have an odd degree with a positive leading coefficient. So if you recall, that's going to take on the shape of x cubed at the ends, right? So our end behavior is going to be that of x cubed. Find the zeros of f. So this is where I've got to go back to my algebra skills and solve by factoring if we can. You may have to bring in the quadratic formula, other things within this section. This is 4 terms, so we can factor by grouping. There's an x squared common between the first 2, leaving an x plus 3. There's a negative 9 common between the last 2. Dividing that out leaves an x plus 3. So we find that this is x plus 3 times x squared minus 9 is equal to 0. So we get x plus 3 is equal to 0, and x squared minus 9 is equal to 0. So we have x is equal to negative 3. And remember, x squared minus 9 equals 0. We can use the square root property to get x squared equals 9. So x has to be plus or minus 3. So notice, what are our zeros? They are negative 3 and 3. But negative 3 repeats itself twice, so this has a multiplicity of 2. And then the 3 is just multiplicity of 1. It doesn't repeat itself. So just from that, we already know a lot about the graph. If we think about the zeros at negative 3 and 3, we know the end behavior, so we know it's going to end up somewhere in the first quadrant. It's going to begin somewhere in the third quadrant. Now, what do we know about how it's going to look at negative 3 and 3 related to the x-axis? Well, negative 3 is a root of multiplicity 2, so that means it's going to just touch the axis there. Okay, in fact, if you can think about x squared, right, it's going to look like x squared around that root. Then the 3 is a odd root, if you will, or not, I shouldn't say odd root. It is the multiplicity is odd, so it's going to look like a linear function through there. So it's going to cross the graph through there. So we already know what the basic shape of the graph is going to look like. We need to plot a few additional points just to fine-tune that. So what I would suggest that you do is make a table, and in your values of x, choose, we don't really need to worry about what's to the left of that negative 3 because we already know the basic shape, right? It's just going to continue going down. We might want to look between the negative 3 and 3, so maybe you want to plug in 0. If you want to be more precise, you could plug in like negative 2 and positive 2. But let's just plug in 0. We plug in 0, we would get negative 27. And we already know what's going to happen to the right of 3. So I don't have enough room to put negative 27, so let me count by 3's here. And I think that's 10 units, so there would be a negative 27 down here. So the rough shape of my graph is going to look something like this. Okay. Now I have actually graphed it for you on the graphing calculator and brought that in so that you can see what that is here. Okay, and it actually does dip down below the y-intercept that I found, so just kind of be mindful of that this is just a rough sketch of the graph. But we knew a lot of it just from finding those first few things. Now on my table, just so you can get a feel for my table, I used the standard window between the x, that is -10 to 10, but I took that from -40 to 10. Okay. Let's do one more. And this is f of x equals -4x times x minus 3 squared, cubed, times x plus 2 squared. So it's already in factored form. Let's talk about what the degree is, what the leading coefficient is, so we know what the end behavior looks like, and then the zeros. So what do we know about the end behavior? Well, there is a -4, so when it gets multiplied through by all those x's, it's going to be a negative leading coefficient. The thing that we need to think about is what is the power on x. If we expanded all that, we'd have an x cubed in there, we'd have an x squared here. When you multiply x cubed times x squared, you get x to the 5th, and then times another x would be x to the 6th. So we have a negative leading coefficient of an even degree polynomial. So if you think about the x squared flipped over, we know it's going to look like this at the ends. What about the zeros? Well, it's already factored, right? So we really have where -4x equals 0, where x minus 3 cubed equals 0, and x plus 2 squared equals 0. So we would get x is equal to 0, x is equal to 3, x is equal to -2. Notice our multiplicities. This is a root of multiplicity 3, and -2 is a root of multiplicity 2. So now if we want to, let me do something real quick here, get a graph. Let's get the general shape and then I'll show you on the calculator. So we know what's going to happen here. We know that we have a 0 at 0 and at 3 and at -2. Okay. Now, what's it going to look like at each of those zeros? Well, 0 just repeats once, so it's an odd multiplicity, so it's going to go through at 0. 3 is an odd multiplicity, so it's going to cross the x-axis at 3, so it's going to cross the axis at both 0 and 3. And what about at -2? It's a multiplicity of 2, which is even, so it's going to touch the axis there. The other thing we know is the end behavior is going to be down on both sides, right? So we can really kind of get the shape just by knowing that. It's going to have to touch at -2, so it's going to go down to some point, and then it's going to have to come back up to go through 0, and then cross back down. So we know the basic shape. We would have to fine-tune that obviously with the graphing calculator. Oops, let me clean this up just a little bit. So let's see, if we wanted to do this on the graphing calculator, what would it look like? Let's clear this out and we can input -4x times a quantity x minus 3 raised to the 3rd power times x plus 2 squared. Okay, and graphing that. Okay, that graph was a window that I had previously for the other function. So let's try to think about what we need to do for this window. Notice at -3 it's already going down to -2500. So it's getting down very quickly. Between -2 and 0 it's going to -256 up to 128, 288. So our x values don't need to change because our zeros are located between -10 and 10. It's our y values that need to change. So let's just do like -1000 to +1000. and let's have a scale of 100. Okay, so there is the basic shape of that graph. So we knew it touched at -3, at -2, it's kind of like a quadratic there. And then at the 0 and the 3, it was like a linear factor or a cubic factor there. Okay? And if you wanted to be more precise, you can use the table like we just looked at to try to determine the window to get some precise points that would be on the graph. Okay? So really using that leading coefficient test, the ability to find zeros, and testing additional points if you need them. That's what polynomial functions is all about. So if you have any questions, don't hesitate to contact me. Thanks.